Okay, group, General Chemistry 2. This is the PowerPoint lecture for Wednesday, February the 17th. I'm recording this on Monday the 15th. There will be a little bit less information today than there was, or for Wednesday than there was for Monday, simply because, we covered a lot of stuff. So take your time, go through all the mechanism stuff. We're going to finish up mechanisms and talk a little bit about nuclear chemistry today. As far as the announcements go, again, don't forget that Alex, the second half of chapter 14 is due on Thursday, tomorrow night. This is the last of the kinetics. Lab 2 this week, so be prepared for that. I was talking to my in-person class today, and one of the things that I wanted to let you know is for lab this week, be sure that you're prepared. Know where you're going. There are a lot of solutions that you're going to need to prepare. And after you've gone through the process a couple of times, you need to be pretty efficient about how you go about that. When I mean efficient, I mean, hey, you know the technique, you can do the pipetting, you can add from a burette, you can do all of these things and gather your solutions pretty quickly. All right, and then of course, don't forget that we have our exam coming up on Thursday and Friday. Thursday for the online class. One shameless plug. This is if the J-term trips go. I've been involved in developing the Science and Technology in New Zealand course. The Opportunity Fair is coming up in 2 or 3 weeks. So I think it's on early March. So I just wanted to point this out that if you're interested in going, it's a phenomenal trip. We're gone for 27 or 28 days, or 27 days, I think, 26 or 7. And it is an incredible experience. It's science and technology, but it's also all kinds of science and technology. It's history, it's architecture, it's politics, it's the seas, it's farming, it's glaciers, it's all of those things kind of rolled into the culture of New Zealand. And so it's quite a trip. So I'm just throwing it out there so that maybe you can keep it in the back of your mind. If you go to the Opportunity Fair, please stop by and talk to me. Dr. Maddox, Dr. Trey Maddox and I are teaching the course, planning on teaching the course in January of 2022. And what would a regular class day be without some despair? Helps artists die young, miserable, and penniless so their art can have meaning to the old, satisfied, and obscenely rich. Or Van Gogh. Some places remain unknown because no one has ever ventured forth. Others remain so because no one has ever come back. Yeah, if we really cared for the customer, we'd send them somewhere better. Several business-related theme slides throughout the slide deck. Here's another one. Because we're not satisfied until you're not satisfied. Actually, that is the theme for despair.com. When birds fly in the right formation, they need only exert half the effort. Even in nature, teamwork results in collective laziness. For every winner, there are dozens of losers. Odds are you're one of them. Ouch. Ooh, I felt that one. There's no greater joy than soaring high on the wings of your dreams, except maybe the joy of watching a dreamer who has nowhere to land but in the ocean of reality. All right. I'm just going to check this to make sure that we're getting the full screen. Okay. So we're only going to finish up a couple of kinetics topics, and then we're going to be moving into a little bit of nuclear chemistry. Know that what we're going to talk about with nuclear chemistry relates really to kinetics. So let's take a look at this. We've been talking about mechanisms. I just want to tag on to what I was talking about in the last lecture. Oh, by the way, I did send an email out about in the last video I had come to an incorrect number. That's what happens when I do the calculations on the fly. I think the number was like 0.09. It should have been 0.74. 0.74 was the number, and I think that was for the, I want to say it was for the second order rate law calculation, about halfway through the last lecture. Anyway, you'll know where it is. Unless you haven't watched any of the videos, in which case you wouldn't, and in that case, it's probably irrelevant anyway. All right, so here's the reaction. 2A plus B goes to C as the following proposed mechanism. So as we look at these two elementary steps, notice that we have A, B, D, and C. So what do we call D? Yes, I heard that. It is an intermediate. It's formed and then subsequently used up. So let's write the rate law for this reaction. The first is a fast equilibrium. The second mechanism step, the second elementary reaction, is the slow step. Remember, this is K1, the rate going forward, K minus 1, the rate going back, K2, let me back up. K1 and K minus 1 are the rate constants for the forward and the reverse equilibrium reactions. I'm gonna wait until that pops here. There it goes. Okay. The slow step, this is K2, K1, and K minus 1. The rate is equal to K2 times D. Yep, that's it. Times D times B. For the slow step of the mechanism, for the slow elementary step of the mechanism, the rate law applies. Coefficients become exponents. Here's our rate law. But we can't have D in here because D is an intermediate from reaction step 1. So we take the first equilibrium and rearrange it. So the rate forward for the first reaction, the rate is equal to K1, A, B, and that's equal to K minus 1, B. The rate forward, A, B, K1, rate forward is equal to the rate reverse, K minus 1 times D. So we want to solve for D, substitute all that mess in here. So D is equal to K1, oops, that's minus 1. Apologize for that. That's what happens when I'm not paying attention. D is equal to K1 over K minus 1 times A, B. So what I do is I take all of this and substitute it right here for D. If D is equal to that, let's just plug it right in. K minus 1. So all of this comes in here in place of D, and then on the back end we have B. So our rate law becomes all three of these we roll into 1K, one generic constant, A, and there's two of them, so it's B squared. So our overall reaction, this is the rate law. First order in A, second order in B. And we do this because we can't have an intermediate in the rate law. So we have talked about pretty much everything related to kinetics at this point. Pretty much all that we're going to need to do. We talked about how to look at the rate of a reaction from concentration time data. So as we have that concentration decreasing, we can find the rate at any point, rise over the run, the slope of that line. We looked at the mechanisms, well, how molecules have to collide with enough force and with proper orientation in order for them, the molecules to form a transition state at the top of the hill. At the top of the hill, that's the activation energy that has to be overcome in order to get there. The transition states at the top, it could go back to reactants or forward to products. Remember that if our energies are like this, higher to start with, lower at the end, the gap is delta H, exothermic, endothermic. So if we end up having our system absorb more energy, then that's an endothermic process. Mechanisms of catalysis. So let's say we have a solution and we have a reaction going away. And if we add a drop of something that's already in the same phase, a good example of this would be an aqueous ion, let's say a metal cation that we add to the solution, and then the reaction might really take off. That would be an example of a homogeneous catalyst. It would be like, let's say we have a reaction taking place in water, and then we throw an aqueous solution of a catalyst in there. It all mixes in, it's totally uniform, homogeneous, and it would be a homogeneous catalyst. Very often, so here's the difference between a homogeneous and a heterogeneous catalyst. Let's say that we have a solution taking place in solution, and we put a steel bar in there and hold it. Maybe steel's not the best thing. Maybe it's maybe it's not steel. Maybe it's platinum or some other kind of metal. And the reaction just really takes off because now it has a surface on which it can react. So that would be an example of a heterogeneous catalyst. Homo means the same. Hetero means not the same. Okay, that is it for chapter 14. We're done with chapter 14. And we're moving on to nuclear chemistry. The reason we're moving on to nuclear chemistry right on the heels of kinetics is because we use kinetic mechanisms in nuclear kinetic processes, kinetic calculations in nuclear chemistry. How fast does radioactive decay take place? That's a kinetic process. Nuclear chemistry, and by the way, we're not going to spend much time on this. We're just a little bit. We're going to cover a few topics from chapter 20. And this is where we start. All of the chemistry that we've done up to this point, we look at enthalpy of reaction. We talk about solution chemistry, the kinds of reactions that take place. We have precipitation, acid-base, and redox reactions. The fundamental kinds of reactions that take place. All of those reactions, the chemistry that's involved there, occurs with the electrons. In certain cases, it's in acid-base reactions, it's transferring a hydrogen ion. In the case of redox reactions, it's transferring electrons from one thing to another. We're talking about the structure of atoms and molecules and how the electrons are arranged. Does this thing want to give away electrons? Does it want to gain electrons? It's about forming bonds that contain electrons. Every single bond involves 2 electrons. In nuclear chemistry, we're not talking about the electrons at all. We totally ignore the electrons. We're looking at the nucleus itself, just the nucleus. Nuclear chemistry is a whole world unto itself. There is a lot of nuclear chemistry that happens in usually at various national labs, Pacific Northwest National Lab, Argonne National Lab near Chicago, Oak Ridge National Lab in Tennessee. There are large research groups at many of these places that are looking at nuclear chemistry.
I think Dr. Rowley is next
Okay,
door.
so actually I'm right here.
Oh, he's in here.
That's okay. So we have these four particles, and these first three are the most common in nuclear chemistry. An alpha particle is actually a chunk of 2 protons and 2 neutrons. So that's the alpha particle. The beta is just an electron, but it's an electron that comes from the nucleus. Now you might be saying, well, there aren't any electrons in the nucleus. But think of it this way. A neutron and a proton are almost the same size. They're almost the same mass. A neutron is very slightly larger. And in fact, a neutron is the combination of a proton and an electron. So if we jam an electron onto a proton, we add a tiny bit more mass and we neutralize the charge and we have a neutron. So that's a beta particle. It is simply an electron, but it's connected with the nucleus. An alpha particle is the heaviest. 2 protons, 2 neutrons, it's a chunk. It's a helium nucleus. It's called alpha. Beta minus is simply an electron. And then gamma, you know what gamma is, way back in chapter 3. We talk about the interaction of light, electromagnetic radiation with matter. A gamma ray is what happens when you have a nucleus that reorganizes. And when it reorganizes, it emits energy in the form of gamma radiation. You can't detect gamma rays and say, oh, that's a gamma ray. All we know about gamma radiation is that it's very high energy and it comes from the nucleus. The region of gamma radiation overlaps the region of X-rays. So very, very, very high energy. You can't distinguish an X-ray from a gamma ray. It's light. It's electromagnetic radiation. The difference is where they come from. X-rays come from rearrangement of electrons around the nucleus of an atom. Gamma rays come from nuclear reorganizations. Again, X-rays come from the electrons. Gamma rays come directly from the nucleus. A positron is an electron that has a +1 charge. It's exactly like a beta particle with the opposite charge. Positrons aren't as common, but they are important for certain applications. You may have heard of PET scans. You can go in to a hospital or clinic, and they can run a PET scan. It's positron emission tomography, PET. And so they actually use positrons from radioactive isotopes to do that kind of imaging. Balancing nuclear reactions. So here are different types of radioactive decay. What decay means is that a nucleus, usually a heavy nucleus, reorganizes, like uranium, which has 92 protons. That nucleus reorganizes, and when it reorganizes, it spits out a particle, in this case like an alpha particle or a helium nucleus. Whenever this happens, it almost always additionally kicks out a gamma ray. When you balance an equation like this, notice that there's one of each. And what happens is you have to balance the total atomic number, which is the total number of protons, and you have to balance the atomic mass, which is the protons plus neutrons. So for balancing nuclear equations or nuclear reactions, we have 92, and we know that this is 2. Well, this just has to be the difference between the 92 and the 2, since it's on this side. Same thing with the mass, 238, that's equal to 4 plus 234. For something that emits a beta particle, it's emitting an electron, a -1 charge from the nucleus. This is what happens when a neutron converts into a proton. When a neutron converts into a proton, it kicks out that beta particle and It increases the nuclear charge by 1, which changes the nature of the element itself. Here we go from thorium to protactinium. Try saying that 3 times really fast. Protactinium. So we have this that emits a beta particle. This is -1. A nuclear electron, this goes up by 1. The mass stays the same because this, relatively speaking, the beta particle has no mass. It does, but it's insignificant. Okay, so gamma ray production. We looked at this reaction earlier. There are actually 2 gamma rays associated with that. This is a positron. This is actually +1 instead of -1 for this specific reaction. Notice that for positrons, we tend to work with lighter elements. Beta particles typically heavier elements. And one that we're not going to do anything more with other than to show you now, electron capture. So in this particular case, a mercury isotope 201. By the way, you remember what isotopes are, right? You do? Really? Sure. Okay, isotopes. Same atomic number, different atomic mass. Same number of protons, different numbers of neutrons. Those are isotopes. Here's an isotope of mercury that absorbs a beta particle and becomes gold. So this is turning mercury into gold. It is not very efficient, and you're not going to make a lot of money at it, but it is a process that happens at the atomic scale. All right, so try this at home. Notice that we don't have any numbers down here at the bottom. So look them up. What's the atomic number of tin? I think it's 50. A beta particle? It's emitting a beta particle, so this is going to be 0 mass, relatively speaking, -1. Remember that a proton and a neutron are in the neighborhood of 1,800 times the mass of an electron. So is the mass really 0? No, but relative to that of a proton or a neutron, it is essentially 0. Here, we're looking for a specific isotope. And I'll just do one for you. So this is 126 tin. So it's 126 SN. I'm doing this from memory now. I'm pretty sure that the atomic number is 50. If it isn't, well, the way it is. Gives off a beta particle. What do we have left? This goes from 50 to 51. Whatever element 51 is. This is why I should have memorized the periodic table. Let's see if I can. Sure. Hang on, you can speed this up. Just looking for my periodic tables. Here we go. Oh, I do have one. Yep, got it. Okay, tin is 50, 51 is Sb, antimony. So 51 minus 1 is 50. Those are balanced. And then for the mass, 126, 0, 126. That's all it is. That's the answer. Balancing nuclear reactions is easy. Let's look at this one down here, 234 thorium. And thorium is number 90. Notice for some of these elements, they're way down at the bottom of the periodic table. Okay, see that? Here's my beautiful periodic table. All right, glad you can see all those numbers on there. Now, that is forming 234 Pa. Keep in mind, you'll always have a periodic table available. Pa has atomic number 91. So what are we forming in addition to protactinium-234? Hey, the mass is the same, pretty good bet it's going to be a nuclear electron. And yes, 90 goes to 91 plus -1. Okay, that's it. Balancing nuclear reactions. You can look at the other two, and those involve alpha particles. Okay, for a radioactive decay series, what happens is this. Look at the periodic table. Look at your periodic table. As you look at the periodic table, let's look at helium. 2 protons, 2 neutrons for the average helium. Total mass of 4. Let's go on down to beryllium. 4 protons, 5 neutrons. Let's go over to boron. It's more like 5 and 6 on the average. 5 and 5 or 5 and 6. Carbon, 6 protons, 6 neutrons. Nitrogen, 7 protons, 7 neutrons for the most part. Oxygen, 8 protons, 8 neutrons. For a lot of these lighter elements, you have a 1-to-1 correspondence, or close to it, of protons to neutrons, or of neutrons to protons. Typically about 1 of each. This is true up until about calcium. So where calcium is on the periodic table, right down here, you have 20 protons and 20 neutrons. 20 protons and 20 neutrons. About that 1-to-1 ratio. After calcium, we end up getting more neutrons than protons. Until we get to the really heavy elements, we have more like a 1.5 to 1 ratio. So we might have something, so if we have 50, if we have like 10 where we have 50 protons, we might have something like 70 neutrons. We have a lot more neutrons than we do protons. When we have these very heavy elements, we get thorium, 232 emits an alpha particle, and we end up with something that's a little bit lighter. That subsequently loses a beta particle, and we end up with a product from it, just like the reactions we were balancing before. The product here undergoes another beta particle emission, and we end up at the end of the chain of the series. This is a radioactive decay series. Here's another one where we're starting with something different. Try practicing this. And what we're going to do is stop here. We'll end the video here, and this is where we're going to pick up after the exam.